Jonathan Samuelson is co-founder and CEO of Divideon, a software development and technology licensing company developing the open source video codec VC. Before Divideon, Jonathan worked as a researcher and project manager at Ericsson. John has contributed to multiple standards, including HEVC, VVC, and most recently, Mpeg-5 Evc, for which he's an editor of the standard and the topic of this conversation we're going to have. Jonathan, please come up.
Thank you very much, Ben, for the kind introduction. This talk will be about Mpeg-5 Evc, essential video coding. So we just heard about HEVC and the level of additional complexity added with that codec, but this one is going one step beyond that. So it's the next generation codec currently being developed within Mpeg. So let's see. There we go. I'd like to first talk about why Mpeg-5 Evc is being developed. And at a very basic level, you'll see that in general, video consumption is increasing globally. If you can improve the compression, you can reduce costs, you can increase quality. And even though HEVC has come a long way since it was released 6 years ago, most video services and streaming services today are still using AVC H.264, which is now a 16-year-old codec, and the technology in AVC is somewhat outdated when you look at the compression techniques that has been developed since then. So there is room for a new codec, but there are also different alternatives. So if you take a look at the video codec landscape and the most modern codecs, you have AVC already out there, which is really dominating codec for video conferencing, HDTV, online streaming. And looking at the licensing aspects of AVC, you have one patent pool, which is really covering a large majority of the patents for that standard. While with HEVC, there's a little bit more of a different landscape with multiple different patent pools and quite a few organizations or companies that are not inside of any of these patent pools. So it's quite difficult to make an estimate of how much it will actually cost to deploy HEVC if you don't know how much you will pay in license to deploy it. There is also the AV1 video codec initiative, which started a few years ago. Last year, they produced the final specification for AV1, and this is the royalty-free initiative, primarily driven by Google, but there are quite a few over-the-top service provider companies being involved in that project. But there is still some level of uncertainty whether it's actually royalty-free. There is announcement from Sysvel around a patent pool for AV1. So a certain degree of uncertainty around the royalty-free claims for AV1. And then there is, of course, the VVC, Versatile Video Coding Project, which started in 2015, at least the preparation for that project. And that's really a huge project in collaboration between Mpeg and ITUT. And it's built quite a bit on top of HEVC in terms of technology. You have a lot of new technology being brought in. So there is a little bit of concern that the licensing and patent situation will look quite similar to HEVC, at least at the outset of it. It might be a bit problematic. And then there are, of course, several different proprietary codecs being brought to the market as well. And we have the AVS standards in China, like more region-based codecs. So there are already quite a few different codecs in the codec landscape, and you might wonder what makes Mpeg-5 EVC special, or what's the differentiating factor for that one? So just looking at going a bit more into the details of the HEVC patent holders, this was a graph produced or published at IP Watchdog, where they've tried to analyze the patents inside of HEVC to see who has really contributed technology. And you'll see at the top of those having a large portfolio in HEVC is Samsung, and Qualcomm is really standing out as being key contributors to HEVC. So they have quite large patent portfolios. And what has happened with Mpeg-5 EVC is that Samsung, Qualcomm, and Huawei together has brought in a starting point for this work in Mpeg. So you'll see that it's quite a team of companies which have strong codec portfolios and codec teams. So that's the first kind of differentiating factor for Mpeg-5 EVC. It's really built on a strong foundation of some of the leaders in video compression. Another key differentiating factor is that it will include a royalty-free baseline. So if you scale off all the advanced tools in Mpeg-5 EVC, you will get down to a baseline which only consists of tools which has been either contributed to the project on a royalty-free basis, or which is old enough so that any patent that may have existed has already expired. So technology that is more than 20 years old. And then the third differentiating factor is the framework under which it's being brought to the market, and a clearer and more transparent licensing framework which is under development. So in terms of how this standardization is different for Mpeg-5 EVC compared to traditional Mpeg codecs and compared to HEVC and VVC, so this is a description of the process which is actually part of the requirements document in Mpeg, where it says the base set of tools to build the standard should be either 20 years or older or submitted with a royalty-free declaration. And any additional tool that you put on top of this base set should be bringing significant improvement in terms of compression performance, so that it's actually bringing a large enough gain to motivate it's being included in the standard. And then each additional tool should also be able to be switched off, so you can have this isolation of all the different tools. And if there is some complications with the terms down the road, with a tool down the road, so that you're unable to license that particular tool or the technology included in that tool, you should be able to disable that tool and still use the exact same format, and everything is kind of already defined for how to handle or how to run the codec with that tool being disabled. There's also an encouragement, a clear encouragement to contributors to make voluntary declarations around the licensing terms and their publication. And finally, there's work or a method for the profiling mechanism, so that you can define a profile with a subset of the tools of the standard. So what applications does this new codec really target? It's two of the most emphasized applications is live OTT streaming and offline streaming for video on demand. But it will also address like general video applications, video conferencing, traditional broadcasting. It's being designed to give good performance on emerging video formats such as 8K, VR, high frame rate, high dynamic range, wide color gamut, and so on. So I'm not going to dig that much into the details of the codec. Pradeep showed a very good diagram over how the encoder is operating My figure here is similar, but this is from the decoder perspective, because that's how you define the standard. You define how the decoder operates, giving a certain bit stream. So you'll see a lot of similarities in this diagram to the one Pradeep was showing for HEVC. On a high level, it's really much the same basic flow of the decisions, and basic structure is very much similar. What's shown in this slide, in the yellow boxes, is the baseline version of the Mpeg-5 Evc. In the blue boxes is the main profile, the additional tools that you can turn on top of the baseline profile. So looking at from a decoder perspective, you have a compressed bit stream, you have some high-level syntax which controls how the reference pictures are handled and so on. You have an entropy decoding running. You have the coding structure where you split each picture into these coding tree units. You have both the inter-prediction and intra-prediction, and from a decoder perspective, you have these inverse quantization, inverse transform, where you take the residual from the inter-prediction or the inter-prediction, and you code that, you decode the coefficients and add that to the predicted in order to get your final result for that block. And then in order to make sure that the block in itself doesn't produce blocking artifacts, you'll have these different in-loop filterings, which is, in this case, in the baseline profile, it's a really simple deblocking filter, while in the main profile, it's a bit more advanced. So just bringing up these the acronyms, what they stand for, I will not go into the details of each one of these, but so you can see that the difference between the baseline profile and the main profile is really spread out in all the different pieces of the codec, but each one of them is kind of isolated, so you can turn one of them off and keep all the others turned on, and it doesn't affect the other tools. So there's very little interdependency between these advanced tools. I will give, I don't intend to go through the full list, but I'll give a couple of examples of tools which are really specific to Mpeg-5 EVC. A lot of these tools that you see in the list are either already present in HEVC in some form, or you might see some similar tools in AV1 or in VVC. But there are a couple of ones which are really specific to Mpeg-5 EVC. Here's one which is the split unit coding order, where the encoder has the choice of processing a split unit, a smaller block, in either the traditional left to right order or in a reverse order, right to left. Depending on the content, depending on the structure of the content, you might get a much better prediction if you first encode the block further to the right and then go back to the left. So that's one of the additional choices you will have in the encoder for Mpeg-5 EVC. Another example which I've been working with is the implicit derivation for reference structure. So what you see here is each of these small blocks is a picture in the output order, display order, and you'll see the references to other pictures separated up in temporal layers. So you'll have this hierarchical coding of by-predicted pictures. And there is a scheme in Mpeg-5 EVC to derive this hierarchical structure implicitly, so that you don't have to signal for each picture exactly which reference pictures to use for this picture. It's all derived based on which temporal layer and which order you receive the picture. So those were a couple of examples. What's a bit more interesting, perhaps, is to see how this new codec under development is performing compared to other codecs. So once again, using the BD rate, they calculated as a average difference, how much can you gain in terms of bitrate while keeping the same quality. In this case, the quality is measured in PSNR over 4 different QP values, and then taking the average bitrate reduction over those. So here's a couple of different test sequences and comparing Mpeg-5 EVC main profile with all those tools turned on, and comparing that to the reference encoder of HEVC, you'll see in this case 26% gain in bitrate for the same quality. You'll also see listed here the encoding time increase, or the relative encoding time. So it's five times slower to encode, and the decoder is 1.75 times slower compared to the HEVC reference encoder or reference decoder. For the baseline profile, it's generally compared or tested against AVC to see how much you can gain compared to AVC using the reference encoder for AVC, which is JM. So here you'll see more than 30% bitrate reduction, and actually the encoding time is faster for ETM, the EVC reference encoder compared to JM, while the decoding time is roughly the same. So these were with different baseline, comparing with different anchors. If you compare the baseline profile and see how much gain you get from turning on all the tools in the main profile, you'll see that it's almost 50% gain in BD PSNR. And you can plot this in curves for each sequence. Here's an example with the cactus sequence. You'll see the blue curve corresponding to AVC is the lowest performing. For each bitrate point, it's reaching lower PSNR values. Then you have the EVC baseline, and then you have HEVC, and then you have EVC main. So this is a typical example of how these different anchors, or different tests compared relative to each other. So that's about the results. What we're looking into, I mean, we're spending quite a lot of effort in making sure the codec in itself and the definition and the tools that are included in Mpeg-5 EVC is really strong, there's technical strength, and getting it, doing the work in standardization, making sure it's approved by ISO, ISE to be published. The plan is to have it published during next year. But that's kind of only the start of the project for bringing a codec to the market. So there's also quite a bit of work being done when it comes to the licensing terms to make sure there's a good and open, transparent program for licensing. We have work being started on system integration, how to include this codec into different transport protocols and different file formats and so on. Development on open source software and tools and all of that is also being started in some sense. And then, of course, next steps will be making device support for the codec and actually see the deployment of the codec. So there's a long way to codec success. And that's my final slide. Thank you very much.
Bring up, there we are. Bring up everyone else who want to have some broader questions around the codec universe, which I admit I am unhealthily excited about codecs. It's the best things ever, along with ice cream. So the comparison I mentioned before about between the reference encoder and versus the HM and that, I mean, is that how indicative do you think that is of the can a Delta computer would take a Mpeg-5 encoder to outperform a HEVC encoder in terms of quality of perf?
That's a good question. I think just like Pradeep was mentioning, if you're doing offline encoding and you have the time to actually do a lot of evaluations on the encoder, then I think for that case, the reference encoders are quite indicative of how much you can actually gain. If you take that, you have the ability to do a search on the encoder with quite high complexity. If you wanted to look more towards live encoding and you have this tight speed limit, then I think it's really tricky to get those 25 or 30% gain over HEVC. I would be surprised. I mean, at least not in the short term that you would see any such gains.
Right. And it always takes several years before you start getting a performance thing. Get reasonably fast implementations. Even in the case of X265, which has been around for 6 years now, I mean, we're still seeing significant improvements in performance at a given quality level. So codecs do take quite a while to mature. In fact, we've seen even improvements in AVC encoders in the last 12 months, and even occasionally some MPEG-2 codec improvements too. So we're able to turn, Moore's law makes MIPS, and MIPS make better looking pixels pretty much infinitely. And we could probably spend 1,000 times more compute per pixel on MPEG-2 today than we did when MPEG-2 services first launched. Probably more than 1,000 times more. I don't know. Yeah.
Maybe.
Okay.